Good morning, everyone, and welcome to another Quanser live webinar. This is the launch of Quanser Studios Enhancements webinar. My name is Gemma Wang. I'll be your host and moderator this morning. Today's webinar will be presented by our Director of R&D, Peter Martin, and Director of Sales, Pasha Javid. You will learn about how we have rebuilt our self-driving car studio. We will showcase our revolutionary new virtual QCAR environment that we hope will change the way self-driving is researched and presented to students. You will also learn about our new redesigned Qzone 2.
Thank you very much, Gemma, and hello from Toronto, Canada. It's about 10:03 a.m. here, and wherever in the world you're joining us from, greetings and welcome, and thank you for joining us today. My name is Pasha, and along with my colleagues, we are very excited for today's webinar and have been looking forward to it. As today, and as Gemma mentioned, we'll be sharing some very exciting news and updates on enhancements we've made to our very two popular studios, the Autonomous Vehicle Research Studio, as well as our self-driving car studio. And honestly, over the past few months, you might have seen bits and pieces or teased pieces of information about these if you follow us on social media. But we are very excited to deep dive and share all these updates with you. So without any further ado, I will pass it on to my good colleague and Quanser's Director of R&D, Pete Martin, to start today's webinar.
Thanks, Pasha. Yeah, it's a pleasure to be here. Thanks very much for everybody for coming. We're really excited to share the work we've been doing for the last few months on enhancing the studios with you all. And hopefully this is the first of many future webinars like this, talking about more enhancements and more features and capabilities and studios that we have in the backs of our minds that we'd like to work on in the next few coming months. So this is only a touch point in the progress of our studio work. But we're very excited nonetheless to share everything that we've been working on with you. Just to start with Quanser, just in case some of you are new to Quanser as a company, we've been developing educational and research tools for engineering for over 30 years, I think getting close to 34 years now. We started, as you can see here, with servo systems for control systems applications. The concept from the very beginning of the company, right from our nascent stage of deciding what we wanted to do, was to develop hands-on experiences for students that would really illustrate and bring theory to life, the control systems concepts, so that students would really engage with these systems and really understand how control systems worked and how engineering could be applied to hardware and to future systems when they sort of left their academic careers and moved on into perhaps industry or research. We moved from there through the years to improve our systems, to enhance them, to change their capabilities. You can see here just simply with the progress of the servo, from the very original servos to ones that had different configurations, different applications, different abilities, to ones that were more integrated, to have a more turnkey and an easier application, switching from some of our more complex systems to USB and things like that. And then finally to our current servo platform, the Cube Servo 2, you can see quite the nice progression of technologies and enhancements and capabilities over the years, just simply with the servo. And this is the treatment that we've done with a lot of our different systems, our autonomous vehicles included, which we'll talk about today. So there's been quite a progression over the last 30 years of learning from the academic community, learning from industry and our technology partners to really bring enhancements to even the simple servo mechanism. Finally, one example of that would be now with the virtual platforms we have in here. You can see the virtual Cube Servo being able to take our hardware systems and those experiences that we had wanted students to have really back in the late 1980s and bring them to the virtual world, where students now can have experiences like the ones that they would have had with a physical system, but at home on their laptop or even on their phone, without needing to necessarily be in situ in the lab working with physical systems, although obviously that is always the best configuration for these types of experiences. Moving on from there, we've also over the years developed strong partnerships with a number of different universities all over the world, over 2,000 universities, but these are just some examples of ones where we've really collaborated and been able to build some really exciting programs and exciting capabilities for different universities. Some here working on the first year experience, where we're really interested in giving students those hands-on experiences in their first year so they can really learn what engineering is all about. through things like systems engineering and advanced research and design applications of autonomous vehicles to things like control systems engineering, where we're trying to really bring our systems to every level of control systems from the very introductory stage all the way through to graduate level courses to have a consistent progression on a single platform for students to really learn those concepts and reinforce them on a consistent experiential platform, to project-based learning and full course transformation from first year experience all the way through to graduate school. That we've worked with partners all over the world to bring our systems and bring value to their courses and their programs and really achieve all sorts of different ambitious goals. And then moving on from there, we'll just touch quickly on the innovation of some of our different systems. As I said at the very beginning with the Cube Servo, this doesn't just apply to servos. This has been a progression that we've had from all sorts of different controls applications through to the application of aerospace control, ground vehicles, getting into mobile robotics, dynamic systems and structural monitoring, robotics in its both teaching and research application, and then now with the autonomous vehicles and the virtual labs, the progression has been a healthy one to try to bring these experiences and these research capabilities to a number of different disciplines, not just control systems, but branching out into all of the adjacencies of robotics, mechatronics, machine learning, artificial intelligence, all of the other applications that are now once again going back to the early stages of teaching and research where our capabilities can really shine. And then finally, all of this is enabled through a consistent design philosophy, one that we've refined over the years to be able to deliver systems for all those different disciplines, for all those different applications, for teaching, for research, for all of these ambitious projects that allow our systems to really fit and really bring value to those scenarios. Things like making sure they're highly instrumented and open and customizable so that no matter the application, they have the ability, or you have the ability, to take your algorithm, take your teaching syllabus and apply it to the systems. Electromechanically flexible as well. So if there's an additional capability that you'd like to implement, that's absolutely available so that you can add sensors, add actuation, add experiences for students. Obviously, over 30 years of working with undergraduate students, especially, we're very familiar with the rigors of an undergraduate control lab or research lab. And so they're very reliable and repeatable and robust. That's something we've really leaned on over the years to make sure that our systems can stand the test of time and really bring value and consistent results, not just in their first year, but generation after generation of students. We have a very rich documentation and applications team that's been building curriculum and teaching resources and research examples for a decade now. And they continue to work with our partners and to work with our technology partners to be able to bring examples of teaching applications, both traditional and ones that kind of push into new realms of engineering education, as well as some research examples and research capabilities to our partners so that you have a step forward. You're not just starting from scratch with our systems. It's as easy as it possibly can be to integrate them into a teaching lab and to align them to your syllabus and your textbooks, or to integrate them into a research lab and to implement your algorithms quickly and easily. And then finally, the support and maintenance that comes with these types of systems is something that we also are very proud of, to make sure that you're successful no matter what your challenge or no matter what the situation that you find yourself in. We're always there to help and make sure that everything goes to plan. In terms of the studios themselves, I'm just going to touch really quickly on what a studio is. We've been sort of refining this message a little bit as we've developed the studios over the last few years. And so we have now come to a very fruitful result in terms of what we view as being a studio that we could build on, as I said, for the future. One of the main things we really want studios to do is accelerate teaching and research in modern academic fields. So we'd love to be able to take modern fields of academia, ones that are emerging, ones that are gaining traction in the community, both in teaching and research, and accelerate the ability for institutions to adopt those teaching focus fields. So things like machine learning and autonomous vehicles, self-driving cars, to name the ones that we have now, and now looking forward to the future, some emerging trends as well. We'd love to be able to accelerate the ability for an institution to, both in the teaching and research side, take those technologies and adapt them and make them academically appropriate so that they can be used as a platform for ambitious teaching, as well as one to very quickly realize research goals. They are flexible and powerful, and yet turnkey in terms of the devices we build them around and the infrastructure that we use, so that, again, no matter the discipline, no matter the application, if it's adjacent or complementary to those systems, it is easy and efficient to be able to modify our systems and to be able to achieve those goals and achieve those applications that you have. The academic content is very rich. It's designed by what we would call faculty equivalent staff who have all been in graduate research labs, who have taught courses, who have done graduate level research, who understand the goals and ambitions of these types of scenarios and are able to build tools and examples and application curriculum so that it's easier for our partners to be able to use that as a starting point and not have to develop everything from scratch or to figure out how everything should work and come together before even starting to focus on the work that needs to get done. And then it being said, coming back to the investment side and the value side, we want them to be multidisciplinary, multi-purpose, and multi-year infrastructure investments. We'd love nothing more than for this to be the cornerstone or the center point of a whole progression of applications across different departments, across different courses, across different research groups, so that there's really multi-year, multi-generational value that you can bring to this kind of studio. Moving on from there, this idea of expanding capacity is one we talk about a lot with these systems, where inherently having a studio like the ones that we're talking about can expand teaching and research capacity in that it is a room full of equipment. That's naturally going to give institutions the ability to do more teaching, do more research, because there's now equipment that can facilitate those sorts of research examples or research applications and validation, as well as different types of teaching applications. But beyond the target specific audience that we would have in mind for a particular studio, the components, the resources, the systems we have, they can bridge all sorts of different teaching and research groups. They can go from adjacency to adjacency, from autonomous vehicles to robotics, from robotics to mechatronics, from mechatronics to vision systems, to AI, to all the different adjacencies that are emerging now as we have these more and more complex engineering systems. We'd love nothing more than for these studios to, again, be the starting point for that kind of progression, so that you get almost like a nucleus or a progression from group to group to group to be able to really add value and collaborate and work together on ambitious tasks and projects. And beyond that, the devices and the software are very flexible. So that also helps that extension even into even more domains, not just the devices, the hardware, the infrastructure, but the software as well. And then finally, we ourselves will be continuing to improve, to update, to add capabilities, features, software examples, application examples, and even studios over time to really, again, build and build so that these are really valuable centers of research and teaching that can live the test of time. Excuse me. I'll just pass over to Pasha to move on from here into some examples of that success.
Thank you very much, Peter. And I hope my screen is visible to everybody, because what I want to show over the next few minutes, picking it up where Pete just left off, is a few examples of how our studios have done. And I just want to give a report and a summary on how these studios have done so far and how they've delivered on the promises that they made when they were released back in 2018 in the case of the Autonomous Vehicles Research Studio, and 2019 in the case of the Self-Driving Car Research Studio. So this is actually one of our favorite examples that I want to begin with. We use it all the time. This is from our friends at University of Aalborg in Denmark. And I think this institution was among the first, if not the very first institution that received their brand new autonomous vehicle research studio when it was released. And what was given, or what existed at the time, was simply an empty room that was equipped with this studio infrastructure and our vehicles, and very quickly enabled the professor and his team to start doing tests overnight and come up with an algorithm, as you see, from initial tests on the left to the final application on the right, which is actually carrying a load that is hung from the drone around in a trajectory. And research went on and eventually resulted in publication of two papers, very, very interesting papers, one on inspection, autonomous inspection of wind farms, and another one on deep neural network sensors for visual servoing. And at the end, this is what we were hoping to achieve, which is results and validated results in an accelerated fashion by focusing on the actual research. And we are very proud that the studio was able to deliver on what it promised. But there is also more examples among the community of that accelerate factor that Pete talked about. These are just literally screen recordings from the LinkedIn page of one of our other collaborators, Dr. Yumin Zhang, here at Concordia University, where you can see the posts are actually back from 2018 on the left and 2020 on the right. Very, very quickly after having received the equipment, you can see that, again, the professor and his team were able to get up and running very rapidly and to start producing results. And as can be seen here, also proudly sharing them with the community, which also in turn makes us very proud. And at the end of the day, that's what these studios promise to our users. And over the last 3 or 4 years since the release of these studios, we are very proud to have seen these studios used in various types of institutions, from big to small, and from academic to also some industrial partners that have invested in the solutions and are using them. And overall, again, it makes us very proud to have studios installed around the world globally with the help of our customers and our partner base in 26 countries, 60 plus institutions. And the most interesting statistics for us is the 200 plus research papers. I showed a couple of examples, but there is 200 plus research papers that we at Quanser have been able to keep track of. And these are available on our website, on our research papers section of our website. But I think the actual number of publications out there is probably even more than this. But this is what we have been keeping track of. But at the end, what is always important for us and what's always driven our developments at R&D level is community feedback. So very soon after having released these two research studios, we started to listen very, very carefully to the feedback that the community started to give us after deploying the solutions. And one of the first pieces of feedback was what we were hoping to hear, which is in terms of addressing the research needs of a research group invested in autonomous systems or self-driving technologies, the solution actually does a great job in terms of delivering its promise, as we saw in the couple of examples that I showed. So our response to that great feedback is fantastic. We'll continue doing the same thing, and we'll continue improving our research capabilities, as Pete said, by enhancing and having regular periodic enhancements applied to our studios to keep up with addressing the research needs of the community. But the second piece of feedback that we heard very loud and clear was this rise in demand for teaching capabilities around autonomous systems and self-driving. We came across a lot of our users who had been asked by their departments to start to introduce courses at undergrad level around autonomy, around self-driving vehicles, and that need came to come up more and more as a very often conversation topic. So our response to those conversations was, especially when, as Peter mentioned, because we do have an academic application team that are a team of faculty equivalent engineers that work with the community to develop curriculum and content. We started investigating this need, and we started investigating with the objective of developing contents and capabilities to enable our users who are now invested in the research capabilities of our studios to be able to take that to the next level and also start deploying them in teaching scenarios. And as that investigation progressed, we actually made a second observation, which was, given that these topics are very modern and the need for covering them is just arising, there is actually a lack of a common agreement on what should be the typical syllabus of such courses. Unlike, let's say, control systems, which is a very well-established topic, and there's pretty much agreement all over the world in terms of what should be covered in a first or a second or a follow-up controls course. That's not the case at all when it comes to courses in autonomous driving or self-driving or autonomous vehicles. And as a result of that, we took the lead as community leaders in addressing the need and looking at what are the most industry relevant skills that the students should have once taking these courses. And this resulted in a pretty significant shift even in the philosophy and approach of our own academic application team in developing content, which is now we are really looking at skill-based activities that are industry relevant and have very clear learning outcomes, as institutions and courses are also now becoming more cautious of the learning outcomes of the course. We have made the shift to also develop our content to be really based on specific relevant and industry relevant learning outcomes. Um, as always, another feedback we receive from the community is the limitation of space, time, and budget, which on their own introduce problems on scaling and serving a large number of students. One of our responses to this was the introduction of the virtual Q labs that you'll see in a few minutes when I pass it back to Pete. We do have the virtual capabilities for a lot of our plants, but scaling autonomous vehicle courses and scaling self-driving courses is very, very challenging if you really want to have industry relevant skill-based outcomes. And the virtual element of our technology really, really helps to address that scalability problem. And we are very excited to share that with you today. And last but not least, another very common feedback that we heard loud and clear was the need for software agnostic capabilities, was the need to support not just one, but multiple preferred environments for developing software, such as Python, ROS, MATLAB Simulink, and etc. And our response to that feedback was supporting all of these desired environments under the same studio umbrella and having cross compatibility between those languages. So regardless of what language or what development environment is preferred by our users, we are now very happy to support them all and not be tied to just one or two particular software environment platforms. And taking all of that community feedback into account and coming up with these responses, all of that resulted in the enhancements and updates that have been applied to our two existing studios that I'll now pass it back to Pete to go into the details and actually cover some of those changes.
Thanks, Pasha. Alrighty, yeah, let's talk a little bit about what we specifically mean by responding to some of these cues we've taken from our existing customers and conversations we've had. So for the self-driving car studio, this is the new studio environment for that used to be called the self-driving research studio. As you can tell, we've changed the name ever so slightly because now we are also going to be including not just teaching, but also outreach activities for recruitment purposes for different institutions or different programs where there's a sort of a demonstration aspect to some of the work that's being done for student days or for open houses, or even with some of our partners for going out into the community and trying to teach secondary school students about engineering and things like that. And then finally, we're also starting to bridge a little bit into student competition as well. So this is a multifaceted platform now where all sorts of different activities can be done. So essentially, if you are an existing self-driving car research studio user or you are familiar with the platform, the vehicles themselves have stayed the same for now, but everything else is new. We have new maps, as you can see here. There's two different sizes, one large map that allows for really ambitious applications that can have all sorts of different scenarios, from parking to overtaking to controlled and uncontrolled intersections, all sorts of things like that. Those are complemented in the hardware space with smart traffic lights and signage and pylons and all sorts of different scenarios that you can build to illustrate different research applications or different teaching applications. There's also a smaller map, as you can see there, for, again, smaller spaces or for being able to have parallel groups working on different applications. Again, the smaller map is also nice for doing demonstrations and things like that. So flexibility, but the maps are very easy to roll out, very easy to package up, and very durable, and we really think are a nice contribution to the physical act of using these systems and building scenarios around the physical systems. They also have borders to help with localization. As I said, traffic lights, resources that can be used to build demonstrations or to build teaching and research applications. And also we've updated the personalities in the vehicles a little bit too. So there's a whole lot of different new applications in the physical space. But the real touch point, the real special part, once you look at something like this, where you can see the vehicles moving together, is how they work together. So you can see here, we have 3 different vehicles that are navigating through the smaller demonstration environment. They're obeying stop signs, obeying other indicators. They're moving through controlled intersections with the traffic lights we've built. They can be completely customized. The traffic lights talk to the infrastructure. The traffic lights talk to the vehicles. The vehicles talk to each other. The vehicles talk to the infrastructure. There's a lot of communication going on so that you can illustrate things like moving in a convoy or moving through intersections where different directions have different traffic flow patterns. You can see at the top as a bridge into the virtual environment, these are also represented in the virtual environment. So you can also blend in a hybrid way the virtual and physical environments to show different applications and different scenarios and things like that as well. So there's a lot of capability, a lot of ability to apply all sorts of different algorithms and teaching outcomes to this scenario. In terms of those teaching topics that we provide off the shelf, we start with skills activities. Those are likely the ones that would be available at launch. Things like how to use cameras, interfacing to different sensors, line detection, kinematic modeling of a vehicle, occupancy grid mapping to start getting into aspects of obstacle avoidance and localization, sensor interfacing, as well as longitudinal control. So everything you really need to start as a building block, as a foundation for being able to understand the aspects of self-driving. In addition to that, as a complementary way to build out more teaching scenarios that you can rely on for students, there's a number of code examples that will eventually be built out into a more sort of student-like exploratory application for the curriculum package. Those start to take those low-level skills of low-level systems and build up application scenarios, build up more capabilities to illustrate how a real self-driving stack would work. Things like object detection, lane detection, classification, sensor fusion, behavioral planning, state machines, path planning, basically everything you need to be able to actually, as we showed in the previous video, move through an environment and as a self-driving vehicle and obey stop signs and traffic lights and other vehicles and things like that. So it's taking the low-level skills and then pulling them together and building out the applications from there. Moving forward, we'd also like to complement those with additional examples of things like parking and convoys and mapping and things like that. So there's a lot that we want to build up over time. The skills activity is what we're going to focus on for now, and those will be based in Python, as well as we'll have some examples of how to implement them using ROS and also obviously using MATLAB Simulink as well. So there'll be a full complement of examples to showcase Python and ROS and MATLAB Simulink. Most of the teaching curriculum itself will be in Python. So we're really trying to build up these examples so that they give students the skills that they're really going to need if they want to pursue further study in these different fields, whether it be in industry or in research. Those examples will be fully complemented, as you saw in the previous slide, by the same examples in the virtual space. We have a complete high fidelity virtual environment we've developed for these scenarios. It was something that we really felt was critical for us to be able to offer teaching resources for self-driving, because obviously having a class of 100 to 300 students and trying to give them all a really meaningful hardware experience would be a big challenge, as well as being able to complement it with scenarios that are difficult to replicate in the real world, things like pedestrians. And so we've built a whole really rich interactive environment where, as you can see here, vehicles can drive around. Those vehicles can have the same stoplights that are in the physical world, the same traffic lights that are in the physical world. They can follow paths that you can now see illustrated on the roadways so that you're getting a little bit of an augmented reality experience. But really using the virtual and the physical, depending on the scenario, depending on what you want to show, can be equivalent. You can take students and have them develop their algorithms, develop their experiences and their understanding of how these systems work at home in the virtual environment. And then once they have a validated algorithm or a validated approach that they want to validate, they can move to the studio in the real world and they can validate that on the physical systems. And so it's a really efficient way to have students manage their time, to have large groups of students manage lab times and coordination and things like that, as well as being able to have students explore and have fun and really interact with these systems without having to be limited to particular lab sessions or particular scheduling. They can really engage and explore and have fun with these systems in an open way. Um, as you can see here, we've also augmented these virtual environments with all sorts of other applications that aren't quite as easy to do in the real world. Things like different weather conditions, nighttime, daytime, snow, rain, different types of physics interactions in terms of changing friction coefficients or the ability for things to interact in different ways. We have the ability to create environments and scenarios that are different from the real world, things like creating different types of obstacles or animals that are straying into the road, pedestrians that are walking in different directions. So you can really build a rich scenario that you can have students explore and really understand how their algorithms, their approaches to solving the challenges of self-drying would behave in that type of environment. And again, as much as possible, we're trying to have the core algorithms that are developed be ones that could then very easily be ported to the physical studio, and then even hopefully ported from there to the real world, to real world applications that they might see if they're applying these algorithms in large scale, let's say. Moving from there to the Q drone. The Q drone is another exciting addition that we've made to our studio. In this particular case, it's kind of the opposite of the changes we've made to the SDCS studio. In this case, for the Autonomous Vehicle Research Studio, what we've done is changed the vehicle, but the vehicle studio has stayed the same. So if you have the self-driving studio, that's all new, but the cars have remained the same cars we had previous. In this case, the drone is a completely new platform, but the actual vehicle studio that it lives in has stayed the same. And this particular drone, we've tried to really bring a lot of value, a lot of really exciting applications to what you can do with this drone, much more than you could before. Again, as Pasha said, we've listened to feedback from the community to try to offer the ability to do much more than you could previously with this system, to really give the ability to have really exciting applications for different types of research, especially ones that are specialized in sensors. I have one right here, so you can see it in person on my camera view. As you can see, what we've really done is created what we like to call a research grade embedded supercomputer that happens to fly. So it has a full NVIDIA GPU and CPU combination. It's what they would call an embedded supercomputer. It's the Xavier NX. This gives it all sorts of capabilities for doing machine learning, AI, image processing, as well as control and dynamic stability and everything else that you would need out of a drone platform, all completely open and customizable in MATLAB Simulink. Additional interfacing if you want to add your own sensors and your own capabilities to the system, as always, so that you can customize it to your particular needs. But we've also tried to complement that processing power by augmenting it with all sorts of other new capabilities in terms of the sensors that are available. So as you can see, we have not just a frontward facing RealSense camera with RGBD capabilities, but also full 360 CSI cameras. So you have the ability to get full 360 vision and process that using the onboard GPU. We also have downward facing cameras to do things like optical flow. That's a global shutter camera, as well as downward facing time of flight and multiple IMUs, multiple sensors on the different propellers. So you can do dynamic modeling. Excuse me, all sorts of different sources of information, sources of really rich data that you can then process on board or efficiently send back to your ground control station to really expand the capabilities of what this type of system can do on its own or in collaboration with other systems or ground control processing and things like that. So we really doubled down on being able to have a flying supercomputer with a rich complement of sensors and capabilities. These are illustrated here, and as always, this is on a durable platform, one that will last for years and years without needing to have extensive maintenance or things like that, should some of those algorithms maybe not quite work out the way that you'd expected them to. We've done quite a lot of durability testing to make sure that this is something that will stand the test of time. And that is, again, complemented, as always, by the full research studio. As you can see here, we have dozens and dozens and dozens of different types of applications that people have explored with the studio. There are a complement of basic examples we start with, so it isn't just, again, as always, a clean slate. We have a full software stack we've developed for this to be able to use the cameras, use the onboard processing systems to do collaboration, to do navigation and localization and movement through the space, complemented by our vision systems, as well as being able to do collaboration with different vehicles. So there's basic examples to get you up and running with your research needs, but also, as you can see here, lots and lots of different collaborators around the world through our partners and the studio community that you can explore to see how other people have used these systems, and we'll start to use the new systems for different types of applications. So what does this mean? Basically, what we'd like to show and what we hope we show today is that the studio is a rich platform, a rich concept for how you can pursue research, teaching, outreach activities, basically all sorts of challenges that you have in the academic community. We've taken our existing studios that have been quite successful, both for research and for some teaching and outreach activities, and we've doubled down on those. We've listened to our community. We've added what we believe would be a very valuable complement to the systems to really bring a lot of capabilities to these. And we are going to do this type of activity moving forward. So more devices will come, more features, more examples, more value overall, with more studios coming hopefully in the future to really take our systems and build, as I said, ongoing investments and value and cross-disciplinary environments where teaching and research can hopefully achieve new levels of efficiency, productivity, and success. We'll now take a break for some questions. If you have any questions, we're happy to hopefully answer those questions. And hope you, thanks for coming. Hope you enjoyed.
Thanks, Pete. Thanks, Pete and Pasha. So we have one question in the chat box. What board can you recommend to make little academic projects? We need someone that can be connect with MATLAB or Simulink.
That's an interesting question. It's one that we've been considering for some of the future studio work that we've been thinking about doing. I mean, it really depends on the level of academic projects. We ourselves, with our complement of software stack and architectures and things like that, have the ability to cross-compile MATLAB Simulink to run on a number of different boards. Things like, as you saw, the NVIDIA TX2 and the NVIDIA Xavier NX, as well as different types of Raspberry Pis. So there's the ability for us to do things like that, and that's all part of our Quark platform. The same is said for the libraries that complement those to work with things like Python and stuff like that. So there's ways that we have used those systems, and through sort of collaboration with our devices, those can be expanded. For something more basic and more starting point in terms of how you could take an academic project and build a board to work with MATLAB Simulink, I believe there are the ability to do something, for example, with the Arduino Mega with MATLAB Simulink off the shelf. So that's another example that you might pursue, again, depending on the level of project that you're looking at. Josh was wondering, how do you, oh, sorry. Matthew is looking at, can the Qdrone and QCar studios be combined into one? Absolutely. Moving forward, our thought is that we would like to start to perhaps have the autonomous vehicle research studio where the drone has traditionally lived be a place where a number of different vehicles can interact, a number of different systems that we have can all sort of achieve heterogeneous teams, ambitious goals, for depending all together in that studio itself. So, absolutely, you can combine the Qdrone and the QCar studios. There's a little bit of discussion we would have to have in terms of making sure that we understand exactly what your goals are to make sure that you have the right complement of studio infrastructure, things like whether or not you need cameras, whether or not you need the roadways and traffic lights and netting and things like that. But absolutely, they can complement each other, and they can do different types of collaborative missions and things like that, where the cars represent one part of a logistics problem and the drones represent a different part of that logistics problem. So we've definitely worked with partners on challenges like that before. That's absolutely doable. Moving on, Joshua is wondering about how you synchronize simulation of real world. There's a number of different ways we do it. Most of it is done through our communications framework that's built on Quark. So our Stream API allows us to synchronize multiple communication paths, most of them done at the moment through wireless TCP/IP communication. So our efficient communication stack that we've built for doing things like teleoperation, we're now repurposing for communication between the drones as well as between the ground vehicles and the traffic lights and the drones and things like that. So all that communication is built on the Stream API through TCP/IP, but also is somewhat expandable to other types of applications if you want to communicate with third-party systems and things like that. There's a lot of options for how you can approach that problem. But the examples that you've seen and the ones that we've been demonstrating are done through TCP/IP communication. And so in terms of the simulation environment, that would be the same. The simulation environment would communicate through socket connections to the software that you're running to illustrate the other examples and scenarios you want to show. There's a little bit of a nuance there in terms of how the dynamic models work, but generally speaking, it's socket connections and TCP/IP communication. One following question from Joshua: how can I implement custom environments? Also with custom non-static elements. There's a little bit of an interesting path there. So basically, the way that we've developed the environment for the Q car, it's an open world in that the cityscape that you saw in the demonstration is one that is completely empty until you populate it with whatever the scenario is that you want to illustrate. So when you first open that world, it's roadways. It's I can actually show you an example to really illustrate this. So you can see here, if I open up, this is an earlier version of the environment, one that was we were testing. But if I open up the environment, you can see here, it's an open world. There's nothing here. You can move through it. You can navigate. You can kind of decide how you want to work with this space. Excuse me. But there's nothing here. There's no cars. There's no traffic lights. There's just a blank slate. And so in this environment, then you can populate it with whatever the scenario is that you want to illustrate, whatever the challenges you want your algorithm to overcome. And then you can spawn cameras. You can spawn different types of primitives like spheres or cubes, or different types of animals, different types of pedestrians, obstacles, pylons, traffic lights, signs, everything that you want to build the scenario that you'd like to overcome with your algorithm. So customization through that side in terms of how you want to build that scenario is done through an API that you could access from Python or from MATLAB to basically tell this environment where you want things situated, what you would like them to do, how they should behave, what properties they should have, things like that. But in terms of this starting environment, that's one that's static. So you can't, for instance, take this and build a jungle or space. The context of the cityscape is static, but then you can populate it with the elements that we have exposed through our API. Just jumping back to the chat. We provide dynamic models for the car and the drone. We provide the mathematics for a dynamic model of the drone. I believe that's what we have at the moment. I'm not entirely sure if we have one implemented as a real-time model in Simulink. I'd have to check into that. But we do have dynamic models of the drone, at least the previous generation of the drone, and I'm sure we'll work on with some for this one. So you have a starting point for how to model it dynamically. For the car, we don't have a dynamic model of the car as of yet, because of the size and the way that it sort of behaves in the 1/10 scale environment. The dynamics aren't as critical as they might be with a real full-size vehicle. Most of the time, we do a lot of our planning and control of the vehicle using kinematic models. But again, it's absolutely open. If that's something that you want to pursue and try to model and illustrate, that's something that's absolutely doable, given that in both cases, the entire software stack is completely open. Depending on your needs, we can talk further about what's possible there as well. For the Q drone, is there any wind estimation implementation? Can the wind be complemented by the controller? That's an excellent example of something that we'd love to see somebody pursue. We don't necessarily do wind estimation, given that our drones are designed to fly indoors. Typically, there's not a whole lot of external disturbance. Obviously, if you get close to walls or floors, you'll get a little bit of surface effects and things like that. But typically, as our drones are designed to only ever fly in indoor spaces, the environment's very controlled. But that is absolutely something that could be done, given the open architecture nature of the drone. Again, the ability to do that kind of estimation is something I'm sure could be implemented. There was one last question about curriculum development and outreach activities. Absolutely feel free to reach out to us. We'd love to chat about that further. As I said, we have a growing complement of research examples for the autonomous vehicle studio, and teaching and research examples both for the self-driving car studio. And we're building that complement of materials over time. We have now ambitions to partner with a couple of different institutions to work on actual teaching materials for the autonomous vehicle studio. We have other platforms that are coming soon that will even more enrich and expand the materials we have available. So we're working on that all the time, and we'd love to chat more if you have particular needs that we can complement. In terms of the specifics of technical details, if you could reach out to us, we could talk to our specialized team to find out exactly what the capabilities are. I don't know off the top of my head some of the sort of low level technical specificities of how the systems work, but we can absolutely tell you how a lot of that is implemented. Most of that is done through, again, our Quark framework, and so there's a lot of different possibilities there that we can talk about offline. Thanks very much, everybody. This is a wonderful Q&A. Lots of exciting questions.
Yeah, awesome. Thanks, Pete. And I believe that's all. These are all the questions that we have for now.
Oh, one more question. We did
Ross,
talk
yeah.
about Ross. Ross 1 or Ross 2 is an excellent question, as you know, I'm sure. We previously supported Ross 1 for the self-driving car studio. We are now going to augment that with support of ROS 2. So essentially, we'll have at the beginning a node infrastructure available that will show you how to deploy different algorithms to the car using ROS 2, as well as you can either use ROS 1 obviously with the bridge, or our existing materials for ROS 1 will also still be available. But from now on, we're gonna, since we're now developing net new code, we'll be developing for ROS 2. For the drone studio, we'd also love to do some examples of ROS 2 as well. Obviously, for the real-time components, that could be a challenge, and so we're going to have to think a little bit about how we architect the ROS 2 examples to ensure that we have the determinism and performance that we need to actually fly the drone and stabilize it and make sure that it's safe. So there's a few different ways we have in mind for how we'll implement that, but essentially, moving forward, I would guess a lot of our resources, if not all of our resources for ROS, will be based on ROS 2. Thanks very much, everybody. This was wonderful. Feel free, as we said, to reach out to us if you have questions. If you'd like more information, we can be reached at tech@quanser.com, or some of you I know are familiar, so I'm sure you know how to find us as well. Thanks very much.
Thanks, everyone. Thanks, Pete.
Thank you, everyone, for your attendance, and thanks, Pete, for the great presentation and answering the questions from our users. Gemma, over to you to close things up.
Yeah, thanks, Pasha. If you have any questions after the webinar, please visit www.quanser.com or email us info@quanser.com or tech@quanser.com. We'll be happy to have a chat with you. Last but not the least, thank you again for joining us today. Have a great day or great night ahead.